Bismillahirrahmanirrahim. Welcome back with lecture 7 in discrete structures. Today, the, we discuss the previous lecture. This is the previous lecture summary which we discussed in the previous lecture 6, basic concepts of relations, and we also discussed types of relations, relation on a set, and the inverse of relation, and array relations, and representing relations using diagrams. And today's lecture we will discuss about the properties of relations, reflexive, symmetric, and transitive relations, and we will also discuss about the properties of relations, properties of congruence model 3, and transitive closure of relations. These are the basic definitions which we discussed already, and we here recall them. A direct graph or a graph consists of a set V of vertices or nodes together with a set E of ordered pairs of elements of V which are called edges or arcs. The vertex A is called the initial vertex of the edge AB, and the vertex B is called the terminal vertex of this edge. We can use the arrows to display the graphs. We use some like these arrows to show this graph. Here is the representation of this graph in example. Display the digraph with V is equal to A, B, C, and D, and E is the set of ordered pairs binary operations of V by itself, A, B, A, D, B, 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 D, C, A, C, D, and B, D. We have to show A, B, so we show by this diagram A to B arrow, and if here is AD, so it means A to D. This ordered pair BB, so it's B to B. It's also called, this edge is also called a loop. If it repeat by itself, then it's a loop. And if CA, so this from C to A, and CB, so this from C to B, and DB, this is from D to B, and BD from B to D. Now we discuss the properties of relations. We look at some useful ways to classify relations. A relation R on a set A is called reflexive if A belongs to R for every element A belongs to A. Reflexive means which shows a reflection on the original element. So you can see that it's a reflective relation. Are the following we here shows that the following relations on 1, 2, 3, 4 reflexive. So this is the R which makes from this 1, 1, 1, 2, 2, 3, 2, 3, 3, and 4, 4. Is this binary operation R is reflexive? Its answer is no, because 1, 2 is not reflexive, 2, 3 is not reflexive, and if we discuss about this, so you can see here about the reflexive if both of the elements belongs to that. Here are the definitions of symmetric, antisymmetric, asymmetric. A relation R on a set A is called symmetric if BA, an ordered pair BA belongs to R whenever AB belongs to R. And a relation R on a set A is called antisymmetric if A is equal to B whenever AB, which belongs to R, and BA belongs to R. So it is antisymmetric. And a relation R on a set A is called asymmetric if AB belongs to R. It implies that BA doesn't belong to R for all AB belongs to A. So these are the properties of relations. So here we show by these by examples. If here is R 1 1 1 2 2 1 3 3 4 4. This is symmetric because we show that if 1 2 and 2 1 AB belongs to R, it means BA also belongs to R. So these are belongs to R. And if we have to show antisymmetric, so 1 1 is antisymmetric. If we discuss about the asymmetric, then 1 3 3 2 2 1 is asymmetric. You can see from this. And 4 4 3 3 1 4 is also the example of antisymmetric. Now we discuss another definition of transitive. A relation R on a set A is called transitive if whenever AB belongs to R and BC belongs to R, then AC belongs to R. For A, B and C, all the three members belongs to A. So you can say that if AB and BC belongs to R, it means AC belongs to R. This is from the logics. So we have check either the following relations on 1 2 3 are transitive. So 1 1 1 1 1 2 2 2 2 1 3 3. So this is transitive because if 1 2 and 2 2, here 1 2 and 2 2 2 1, so this goes from 2 1 2 1 is also a 1 2 to 1, so 1 to 2 is also here in this R. And if we discuss about this 1 3 3 2 2 1, it's not transitive because if there is 1 3, so there is no ordered pair of 3 1. So we discuss about 2 4 4 3 2 3 4 1, so it's transitive because if here is uh, it's not transitive, so sorry, it's not transitive, you can see. Another example, let A is the set 0 1 2 3 and define our relations R, S and T on A as follows. R is this and S is this and T is if this. Uh, what you think about that, is R reflexive, symmetric, transitive, and if is R S reflexive, symmetric and transitive, and what do you think about T is reflexive, symmetric and transitive? Here we give the answer of this. If let A is equal to this and R is equal to this, so the direct graph of R has the appearance shown below. If 0 1 1 0, it's not transitive, it's reflexive also, it's symmetric also. And if we discuss about the S, the direct graph of S has also appearance as shown below. 0 0, its slope here 0 2 0 3 2 3. So it's not reflexive and not symmetric, but it's transitive. Similarly about T from 0 to 1 and 2 to 3. So it's not transitive, it's not symmetric, so it's transitive. Um, Properties of relations, or we can here question how many different reflexive relations can be defined on a set A containing n elements. So Relations on R are subsets of A cross A, which contains n square elements. We already discussed. A reflexive relation, however, must contain the n elements A for every A belongs to A. So consequently, we can only choose among n square minus n is equal to n into n minus n to generate reflexive relations, or 2 raised to the power n into n minus 1 of them. Now we discuss the properties of less than relation. For all xy belongs to R, x relation with y if and only if x is less than y. Uh, Here is R reflexive, B are symmetric or transitive. So R is not reflexive in this. If and only for all it is reflexive if and only if for all x belongs to R, x are x by definition of R. This means that for all x belongs to R, x less than x, but this is false. This means that for all x belongs to x less than x, or this is false. So there exists x belongs to R such that x doesn't less than x. As a counterexample, let x equal to 0 and note 0 is never less than 0 once R is not reflexive. If we define a relation R on R, the set of real numbers as follows. For all x y belongs to R, x R relation with y if and only if x less than y. Is R reflexive, symmetric, or transitive? So here is R is not symmetric if and only if for all x y belongs to R, if x are y, then y relation with x. So by definition of this means that for all x y belongs to R if x is less than y and y, then y less than x, but this is false. There exists x belongs and y belongs to R such that x less than y and y never less than x. As a counterexample, let we take x0 and y1 and note that 0 is less than 1 and 1 is not less than 0. So R is not symmetric. I try to solve here if x less than y, and we define a relation R on all sets as follows. For all x y belongs to R, x relation with y if and only if x less than y. Here R is transitive if and only if for all x y belongs to R, if x relation with y and y relation with z, then x relation with z. So this means by the definition of R, this means that xy belongs to z if x less than y and y less than z and x less than z. But this statement is true by the transitive law of order for real numbers, hence R is transitive. The transitive clear of its relation let A be a set and R a relation on A. The transitive clear of R is the relation RT on A that satisfies the following three properties. Which are these three properties? RT is transitive, R is subset of RT. If S is any other transitive relation that contains R, then RT is a subset of for example, if we take A0, 1, 2, 3 and consider relation R, which is defined on A as follows. R is 0, 1, 0, 1, 2, 2, 3. And then we find the transitive clear of R. If we discuss the solution, or if every ordered pair in R is in RT. So this R is a subset of RT, and thus the directed graph of R contains as follows: 0 to 1, 1 to 2, and 2 to 3. Since there are arrows going from 0 to 1 and 1 to 2, so RT must have an arrow going from 0 to 2. Hence 0 2 also belongs to RT, then 0 2 belongs to RT, and 2 3 which also belongs to RT. So RT is transitive. So 0 3 which belongs to RT also, since 1 2 belongs to RT and 2 3 which also belongs to RT, then 1 3 belongs to RT. So RT contains at least the following ordered pairs: 0 1, 0 2, 0 3, 1 2, 1 3, and 2 3. So by this relation is transitive, hence it's equal to RT. Here we have to note that the directed graph of RT is shown as follows: 0 1, 0 2, 1 2, 2 3, and 0 3. Relations, combining relations. If we discuss about the combining relations, the combining relations are sets, and therefore we can apply the usual set operations to them. If we have two elements, two relations, R1 and R2, and both of them are from a set A to a set B, then we can combine them to R1 union R2 and R1 intersection R2, or we can say that R1 minus R2. In each case, the result will be another relation from A to B. There is another important way to combine relations. We define a composite of R and S. Let R be a relation from a set A to a set B, and S a relation from B to set C. The composite of R and S is the relation consisting of ordered pairs A, C, where A belongs to A and C belongs to C, and for each there exists an element B belongs to B such that AB also belongs to R and BC also belongs to R. So we denote the composite of R and S by this S combination R. In other words, if relation R contains a pair AB and the relation S contains a pair BC, then SR contains the relation AC, which like to be as a transitive property. We give examples for these combining relations. Let D and S be relations on A, which is 1 2 3 4. D is all the elements A B such that B is equal to 5 minus A, or you can say that B equals to 5 minus A, or you can say that A plus B less than 5. So AB, S is a set AB where A is less than B, is a smaller B, and D, so D becomes 1 4 2 3 3 2 4 1, which satisfies these conditions. B is equal to 5 minus A, and S is the solution where 1 2 1 3 1 4 2 3 2 4 3 4. In all these you can see that A is less than B, A is smaller and B is greater. So S combination D, it will becomes 2 4 2 4 and 3 3 3 4 4 2 and 4 3 and 4 4. So D maps an element A to the element 5 minus A, and afterwards S maps 5 minus A to all elements larger than 5 minus A, and resulting in that S combination D, A, B, which where A is 5 minus A is less than B, or you can say that A plus B is equal to 5, is less than 5. These are the partition of a set. A is finite or infinite collection of non-empty mutually disjoint subsets whose union is A. So A is a partition of a set by the subsets A1, A2, and you can say up to A6. So these are the partitions shown here. We can say that AI intersection AJ is equal to empty where I is not equal to J. AI union A2 union up to A6, which will be equal to A. Union of all A1 to A6 is equal to A. We define a relation induced by a partition. Given a partition of a set, the relation induced by the partition R is defined on A as follows. For all xy belongs to A, X relation with Y, if and only if there is a subset AI of the partition such that both X and Y are in AI. We give here examples. Let 0, 1, 2, 3 and consider the following partition of A: 0, 3, 4 and 1, 2. Question is to find the relation induced by this partition. 0 relation 3 because 0, 3 are in 0, 3, 4, and 3, 0 is also from 3, 0 are also from 0, 3, 4. 0, 4 because both are from 0, 3, 4, 4 relation 0. And 3 relation are also 0 relation 0 because both 0 and both 0 are in this, and 3 are 3 also because it from 3 0, 3, 4, and R by R because both are in 0, 3, 4. Since 1 is a subset of the partition, so 1 relation 1 because both 1 and 1 are in this, and since 2 is the subset of partition, so 2 relation 2 is also because both 2 are in 2. Hence 0, 0, 0, 3, 0, 4, 1, 1, 2, 2, 3, 0, 3, 3, 3, 4, 4, 0, 4, 3, and 4. So this is the R. So you can say that. Now we discuss about the relations, equivalence relations. Let A be a set and R a relation on A. R is an equivalence relation if and only if R is reflexive, symmetric, and transitive. If R is equal to 0, 1, 2, 3, 4, for all xy belongs to A, X relation with Y, if and only if there is a subset of AI of the partition such that both X and Y are in AI. So this is R. 0, 0, 0, 3, 0, 4, 1, 0, 2, 2, 3, 0, 3, 3, 3, 4. R is reflexive, symmetric, and transitive. Equivalence of digital logic circuit is an equivalence relation also. Let S be the set of all digital logic circuits with a fixed number n of inputs. So we define a relation E on S as follows. For all circuits C1 and C2 in S, C1 the relation C2 if and only if C1 has the same input. or output table as C2. If C1 is in relation with C2, then circuit C1 is said to be equivalent to circuit C2. We prove that E is an equivalence relation on R. So here is the proof. Since E is reflexive, suppose that C is a digital logic, and it must be show that C relation with C. So certainly C has the same image as itself. Thus, by definition of E, E is symmetric and E is transitive. Suppose C1, C2 are digital logic circuits in S, and such that C1 is in with E1, C2. We must show that C2 is C1. So, by definition of the relation E, since C1 is C2, then C1 has the same input or output table as C2. It follows that C2 has the same input or output table as C1. Hence, by definition of E, C2 E C1. E is transitive. Suppose C1, C2 and C3 are digital logic uh, circuits in S, such that C1 E C2 and C2 E C3. So we must show that C1 E C3. So by definition of E, since C1 E C2 and C2 E C3, then C1 has the same input or output table as C2, and C2 has the same input or output table as C3. It follows that C1 has the same input or output table. So by definition of E, C1 E C3. Since R is reflexive, symmetric, and E is in relation on S. Let A is equal to 0, 1, 2, 3, 4, and define a relation R on A as follows. R is 0, 0, 0, 4, 1, 1, 1, 3, 2, 2, 3, 1, 3, 3, 4, 0, 1, 4, 4. The directed graph of for R is shown as below. 0 to 0, its slope here, 4 to 0, 0 to 4, 4, 4. So this loop shows this 1 to 3, 3 to 1, 3 to 3, 1 to 1. So it's 2 to. So find the equivalence classes of R. So R 0, 0, 0, 4, 1, 1, 1, 3, 2, 2, 3, 1, 3, 3, 4, 0, 4, 4. We have shown these in the previous slide. I put a pen so 0. Now first find the equivalence class of every element of A. 0. X belongs to A such that X relation with 0. So it's 0, 4. If we take 1 and X where X belongs to A and such that X relation with 1, so it's 1, 3. Similarly for 2, so it's 2, and for 3, X relation with 3, so it's 1, 3, and with 4, this is 0, 4. We note that 0, 4 and 1 and 0 is equivalent to 4, and 1 and 3 are equal. Thus the distinct equivalence classes of the R are 0, 4, 1, 3 and 0, 4, 1, 3 and 2. An equivalence relation on set let X be the set of all non-empty subsets of 1, 2, 3. then x is equal to 1 2 3 1 2 1 3 2 3 and 1 2 3. This is the relations subset. We define a relation R on X as follows. For all A and B in X, A relation with B if and only if the least element of A equals the least element of B, we prove that R is an equivalence relation on X. R is reflexive, so suppose A is non-empty subset of 1 2 3, we must show that A is in relation with A. So it's true to say that the least element of A equals the least element of A. Thus, by definition of R, A is in relation with A. And X is this. For all A and B in X, A relation with B, the least element of A equals the least element of B. So prove that R is an equivalence relation on X. R is symmetric. So suppose A and B are non-empty subsets of 1 to 3 and A is relation with B. So we show similarly as we previously discussed that we must show that B is in relation with A. Since A relation with B, the least element of A equals the least element of B. But this implies that the least element of B equals the least element of A. And so, by definition of R, B relation with A. So R is transitive. Suppose that A, B, and C are non-empty subsets of 1, 2, 3. So A relation with B and B relation with C. So we must show that A relation with C. Similar case, since A relation with B, the least element of A equals to the least element of B, and since B relation with C, so the least element of B equals the least element of A. So it by the definition of this, the equivalence class of 1 is the set of all non-empty subsets of 1, 2, and 3 whose least element is 1 plus 1, maybe so you can say that 1 1 2 1 3 1 2 3. The equivalence classes of 2 is a set of all the non-empty subsets of 1 2 3. The equivalence class of 3 is a set of all the non-empty subsets of 1 2 3 whose least element is 3. There is only one such set, namely 3 itself. Thus 3 is equal to, since all the non-empty subsets of 1 to 3 are in one of equivalence classes, so this is complete. This Suppose A is set and R is in equivalence relation on A, and A and B are the elements of A. If A is relation with B, then A equal to B. Let A be a set, let R be an equivalence relation on A, and suppose A and B are elements of A such that A relation with B. We must show that the class of A equal to B. Prove that A subset of B, let X belongs to class A, and we must show that X belongs to B. Since X belongs to A, then X relation A by definition of the class, but A relation with B by hypothesis. Thus, by transitive of R, hence X belongs to B by definition of the class. Now we prove that B subset of A. Then, if as we discussed previously, if both are the subsets of each other, then they are equivalent. then let x belongs to b. We must show that x belongs to a. Then since R is transitive and x belongs to x relation with b, since x belongs to b, then x relation b by definition of the clause. Now a relation b by hypothesis. Thus, since R is symmetric, so b relation R also. Then since R is transitive and x relation b and b relation a, so x relation a. Hence x belongs to a by definition of class. This is what was we have to be shown. So it means b is the subset of a. Since both are the subset of each other, so it follows that both the classes are a and b are equal. So this is the set by definition of set equality. Here is the theorem. If A is a set and R is an equivalence relation on A and P are the elements of A, then either A intersection B equal to phi or A equal to B. The statement of the theorem has the form if P then Q or R in the logics. Where P is a statement, A is a set, R is an equivalence relation on A and B are elements of A. Q is the statement A intersection B is equal to phi and R is a statement, so A is equal to B. To prove the theorem, we will prove the logically equivalent statement. If P and not Q, then R. That is, we will prove the following. If A is a set, R is an equivalence relation on A and elements of A. So, and A intersection B is equal to phi, it means then A is equal to B. Suppose A is set, R is an equivalence relation on A. A and B are elements of A and A intersection B is not equal to phi. We must show that A equal to B. Since A intersection B is not phi, there exists an element x in A such that x belongs to A intersection B. By definition of intersection, x belongs to A and x belongs to B, and so x relation A and x relation B by the definition of class. Since R is symmetric and being an equivalence relation, and x relation with x relation with A and A relation with x, but R is also transitive. So since it is an equivalent relation, and so A relation with x and x relation with b, so A relation with b. Now A and B satisfy the hypothesis of the previous theorem. Thus by the theorem A is equal to b. What are the relation of congress? Here we discuss about the equivalence classes of congress modulo 3. Let R be the relation of congress modulo 3 on the set Z of all integers. So that is for all integers m and n. M relation with n if and only if m minus n divisible by 3. M congruent to 3 mod 3. M congruent to n mod 3. Describe the distinct equivalences classes of R for each integer a equal to x. X belongs to Z for all the x relation with R, and x belongs to Z such that 3 divides x minus a. So x minus a is equal to 3. K for some integers k. So therefore A is equal to x belongs to Z, and x is equal to 3k plus A for some integer k. In particular, 0 is equal to, you can say that x belongs to Z, x is equal to 3k plus 0 for some integer k, and it's equal to x plus x is equal to 3k for some integer. So these are minus 9, minus 6, minus 3, 0, positive and negative sides. And if we take 1, which x belongs to z, such that x is equal to 3k plus 1 for some integer k. So it's 1, 4, 7, 10, minus 2, minus 5, and if you go in the left side, this will become minus 5, minus 8. And similarly for 2, x is equal to 3k plus 2 for some integer k. So it's 2, 5, 8, 11. In the negative side, minus 1, minus 4, minus 7. Now since 3 relation with 0, so 3 equal to 0. More generally, by the same reasoning, you can say that 0 plus is equal to 3 and it's equal to minus 3, and 6 is equal to minus 6, and so on. So similarly, we can say that 1 is equal to 4, 4 is equal to minus 2, and 7 minus 2, and 2, 5, 8 minus 1, 8 minus 4, and so on. Notice that every integer we here notice is every integer is in class 0, 1 or 2. Hence the distinct equivalence classes are x belongs to z such that x is equal to 3k for some integer k, and x is equal to 3k plus 1 so for some integer k, and x is equal to 3k plus 2 for some integers k. In other words, three classes of congruence modulo 3 are the set of all integers that are divisible by 3, the set of all integers that leave a remainder of 1 when divided by 3, and the set of all integers that leave a remainder of 2 when divided by 3. So the 0 class is equal to 0, 3, 6, 9, minus 3, 6, 9, 1, 4, 7, and minus 2, minus 5, minus 8, 2, 5, 8, 11, and these are minus 1, 5, minus 4, 7. So this is the partition of the 0, union 1, union 2. So the intersection of these classes is empty. So here is the congruence of n is an equivalence relation. So if n is any integer with greater than 1, congruence modulo n is an equivalence relation on the set of all integers. The distinct equivalence classes of the relation are the sets 0, 1, 2, n minus 1, where for each a equal to 0, 1, 2 up to n minus 1. So a equal to m belongs to z such that m congruous to a mod n, or equivalently a is equal to m belongs to z such that m is equal to a plus k n for some integers k. We prove here, suppose n is any integer with n greater than 0 or greater than 1, we must show that congruous modulo n is reflexive, symmetric, and transitive. The proof of reflexivity, we suppose a is an integer. To show that a congruent to a mod n, we must show that n, which is divisible by a minus a minus a which is divisible by n, but a minus a is equal to 0, and n divisible by 0 because 0 is equal to n dot 0. Thus, therefore, a congruent to a mod n. Proof of the symmetry, we suppose a and b are any integers such that a congruent to b mod n. We must show that b congruent to a mod n. But since a congruous to b mod n, then for the divisibility a minus b divided by a n, thus by definition of divisibility a minus b is equal to n k. For some integers k, multiply both sides of this equation by minus 1, A definition, both sides of this equation by minus 1 to obtain minus, if we multiply on this, minus a into minus b is equal to minus nk, or equivalently b minus a is equal to n into minus k. That's by the definition of divisibility and divisible by b minus a. That's the definition of congruous modulo n, b congruent to a mod n. Suppose n is integer. An integer with n, we must show that the congruence modulo n is reflexive, symmetric, and transitive, as we discussed in the previous. So we here prove this by the same method which we used in the previous slides. Here is the theorem. Let a, b, and n be n integers, and suppose n greater than 1. The following statements are all equivalent and divisible by minus b, and a congruent to b mod n, a is equal to b plus k n for some integers k. A and b have the same non-negative remainder when divided by n. A mod n is equal to b mod n. Now we discuss about the modular arithmetic, which is so much important in number theory. Let ABCD and n be integers with n greater than 1, and suppose a congruent to c mod n and b congruent to d mod n, then a plus b congruent to c plus d mod n, a minus b congruent to c minus d mod n, and ab congruent to cd mod n, and a dot m congruent to c dot m mod n for all integers m. As the theorem, let a, b, c, d, and n be integers with n greater than 1. Suppose a congruent to c mod n and b congruent to d mod n, then a, b congruent to c, d mod n. Proof of the part 3. Here we suppose let a, b, c, d, and n are integers with n greater than 1, and suppose a congruent to c mod n and b congruent to d mod n, then there exists s and t such that a is equal to c plus sn and b is equal to d plus tn. Then ab is equal to c plus sn and into d plus tn. So if we evaluate this, CD CTN plus CND plus CN SNTN, CD plus N we take common from this, so it's CT plus CSD plus TN. So this is equal to some K. This will equal to some K. Then K is any integer, and AB is equal to CD plus NK. So AB congruous to CD mod N. It is the verifying the following statements. You can see from this slide. We here shown some verifying statements. You can prove these all statements. Here is also an example. Find the residue of 55, 26 modulo 4. You can see from this, and you can also study it in the number theory. 55 26 mod 4 equal to 55 mod 4 26 mod 4 mod, so it can be written as 3.2 mod 4, because 55 mod 4 is equal to 3.2, so 6 mod 4, which is congruent to 2. We here computing AK and mod n when k is a power of 2. We find 144 power 4 mod 713. We can write 144 power 4 is equal to 144 square whole square. Then this mod 713 is equal to 144 square whole square mod 713. You can write here This 144 mod 73 mod 713, and this can be written in this form because 144 square is equal to this 2736, and this can be written in the form this because 59 square is equal to 3486. So the mod of 3481 and mod 713, it's equal to 629. Here another example, 12 raised to the power 43 mod 713. We can write first of all 43 as in powers of 2. It can be written 2 power 5, 2 plus 3 plus 2 plus 2 power 1 and 1. So this is 32 plus 8 plus 2 plus 1. So next we compute the powers of 12. 12 mod 713, it's 12. 12 square mod 713, it's 144. 12 4 mod 713, it's 1442 mod 3 713, which is equal to 59. And 12 raised to the power 8, which is 592 mod 713, it's 629. And then it will become 12 raised to the power 16, 6292 mod 713, it's 639. And if the same 12 raised to the power 32 mod 713, it's 6392 mod 713, it's 485. So we can solve this example by this. So the answer will be 48. Partial order relations, let R be a relation defined on a set A. R is partial order relation if and only if R is reflexive, antisymmetric and transitive. Here this example, the subset relation. Let A be any collection of sets and define the subset relation on A as follows. For all u v belongs to A, u is subset of v if and only for all x, if x belongs to u, then x belongs to v. We prove that the subset relation is a partial order relation. For the subset relation u subset v for all x, if x belongs to u, then x belongs to v. For the subset to be antisymmetric means that for all sets u and v in A, if u is subset of v and v subset of u, then u is equal to v. But this is true by definition of equality of sets. The less than or equals to relations, which we discussed, for all real numbers x and y in S, x less or equal to y, if and only if x less than y or x equal to y, show that less or equal is a partial order relation. We show that less or equal is a reflexive, is a antisymmetric. Then it can be proved easily. For less or equal to be reflexive means R is reflexive. For this relation to be reflexive means that x less or equal to x for all real numbers x in x, but x less or equal to x means that x is less than x or x is equal to x, and x is equal to x is always true. It's antisymmetric. For less or equal to this to be antisymmetric means that for all real numbers x and y in S, if x is less or equal to y and y is less or equal to x, then it follows that immediately from the definition of less or equal. So it's proved easily, you can see here. It's also transitive. For less or equal to be transitive means that for all real numbers x, y and z, if s in S, if x less or equal to y and y less or equal to z, then x is less or equal to z. This follows that from the definition of the partial and the transitive property of order, which says that given any real numbers x, y and z, if x less than y and y less than z, it means x less than z. Because this is a reflexive, antisymmetric and transitive, it is a partial order relation. Here at the end of this lecture, this is the lecture summary which we discussed today. Properties of relations, reflexive, symmetric and transitive relations, properties of lesson, properties of congruous modulo 3, the transitive closure of relation, combining relations, the relation induced by a partial less or equal. So, thanks for this lecture, and we will discuss with the new lecture, lecture 8, inshallah. We will meet in that lecture. Thank you.